Welcome to this session on Bode plot analysis in control systems. In this video, we will understand what Bode plots are, why they are important, and how to construct them step by step, and how they help us analyze system stability using frequency domain specifications. Now let's see about the why Bode plot matters. So this is the DT empathize part of this video. So in this, let's start with the practical applications. In control system design, engineers often need to quickly evaluate system stability and performance across different frequencies. So without an efficient method, this process becomes time consuming and complex one. So if not properly analyzed means system may become unstable and performance may be degradable and equipment failure may occur. So Bode plots provide a simple graphical method to analyze these aspects effectively. So now let us see the limitations of traditional methods. So traditional time domain methods have several drawbacks. So they are computationally intensive, especially for higher order systems. They do not clearly show how the system behaves at different frequencies. Also, accessing stability margins directly is difficult. Because of these limitations, engineers prefer frequency domain techniques like Bode plots. So for understanding Bode plot, now let's see the definition of the Bode plot. So we can define Bode plot is a graphical representation of a system's frequency response using two plots. The first one is a magnitude plot which shows 20 log of g of j omega versus log omega. The second one is the phase plot which shows the phase angle of g of j omega versus log omega. So these plots are usually drawn using straight lines, approximations called asymptotic plots which simplify the analysis. So the plotting procedure for steps 1 to 3. The first one is a standard form, that is convert to standard formation. Express our transfer function as g of s is equal to k into 1 plus s divided by a into 1 plus s by b, that whole divided by 1 plus s by p into 1 plus s by q. The step 2 is identify slope. So each zero contributes the plus 20 dB for decades. So each pole contributes the minus 20 dB for decades. For example, one pole minus 20 dB per decade and two poles means minus 40 dB per decade. Our step 3 is calculation of initial gain. So at omega is equal to 1 radian per second, the gain is 20 log k. So this gives the starting point of the magnitude plot. Next, the plot procedure for 4 to 5. So fourth one is the find out the corner frequencies. So each corner frequency, a zero increases a slope by plus 20 dB decade and a pole decreases slope by minus 20 dB per decade. For this phase plot, we use the relation the phi is equal to tan inverse of omega by a plus tan inverse of omega by b minus tan inverse of omega by p minus tan inverse of omega by q. So this helps us hedge the phase responses. Next one, the frequency domain specifications. So frequency domain specifications, we are using gain crossover frequency omega gc, that is modulus of g of j omega h of j omega is equal to 1 for 0 decibels. Next, phase crossover frequency omega pc. This is where the phase becomes minus 180 degrees. Next one is the gain margin gm and it indicates how much gain can be increased before instability. Next one is the phase margin PM. It shows how much phase variation is allowed before instability. The stability criterion or the stability condition is if omega PC greater than omega GC, the system is stable. So these parameters are essential for designing a stable control systems. Next we see about the practical applications of Bode plot in control systems, the stability analysis of control systems, filter design in communication systems, motor control system design, and power system frequency response and analysis. So they provide a quick and effective way to evaluate system performance. Now let's move on to the conclusion part of this video, that is Bode plots simplify frequency response analysis, help in understanding system behavior and play a key role in stability assessment. Thank you.